Hi everyone, welcome to IoT again. So today we're going to talk about a very important protocol called. So just to refresh your memory, what we spoke about last class, that in OSI reference model, okay, we start with the physical, right, data link layer, then network, then transport, then the application, right? The application. So usually, for example, in the regular networks, in the application, what we have, HTTP, right?
Yeah.
Right. Examples, right? And many other applications, right? Transport, we have TCP and UDP, right? Okay. And the network layer, we have IP 4 and 6, right? All right. And in physical, right, we have, for example, 802.3, which is the Ethernet, or 802.11, which is the Wi-Fi, okay? Right, so these are, sluggish kind of big protocols. That's why we have to come up with different protocols used for IoT, right, devices. So for example, in the application level HTTP, we don't use HTTP, which is like a sluggish big. We come up with the protocol that we call CoAP, for example. Okay, and as we explained this morning, right? In the transport layer, okay, we try not to use TCP because the sluggish. We use the UDP more, right? Also, in the IP level, in the host level, we have 6 low PAN. IP6 for low devices for personal area network, which we explained last week. And also we have for routing, we have the Ripple, right? We have the Ripple. Also in the physical, we have LLNs, low power, lossy networks, okay? Under the umbrella 802.15, for example, 4 or whatever, right? Example like Zigbee or different kind of Bluetooth devices, small devices, right? So that's what we're trying to do. We already explained, for example, 6LoWPAN. We explained the Ripple. We're gonna go over Zigbee as an example for these devices, right? Okay, and CoAP is a replacement for HTTP. It's a replacement for HTTP. Right? So that's what we are talking about, okay? So it will try to reduce the header and by compression and reduction to reduce the amount of data. All right, so if we need to talk today about CoAP or CoAP protocol, think about it like, it's like instead of typing, for example, HTTP, colon forward slash, whatever, you're gonna write CoAP, like, all right? And there is a plug-in for some of the common browsers. Google does not have them with Google Chrome, okay, but some others have it, a plug-in, right? All right, so let's try. Hopefully, we can explain it, some aspects of it very quickly. So wireless protocols are mainly used for 3 layers: physical layer, network layer, application layer. We already explained that. CoAP is one of that latest application layer protocol developed by IETF, Internet Task Force, okay, the Internet Engineering Task Force, for smart devices to connect to the internet. All right. CoAP is intended to be used and considered as a replacement for HTTP. All right. Still, we need to use HTTP at the big machines, big servers to access it from outside. We could use HTTP. We'll see that we could have proxies between CoAP and HTTP. Proxy, it does the conversion. It does the conversion for being IoT application layer protocol. All right. So let's take a look at the features of CoAP. All right. Overhead and parsing complexity, URI and content type support. So it will be a URI like HTTP, okay, to access the devices. All right. Support for the diversity of resources provided by the non-co-op services. There's multiple services, diversity for different services. We'll see, I'll look at that. Simple subscription for a resource. Okay, what is a resource? Sensor, for example, right? So sensor, in that case, it will be the server.
Sorry, Professor, to interrupt. In today's lecture, you said first we'll discuss project and academy.
No, we're going to discuss the academy and then the project because there is not a lot of people. Okay, so we have the resource. Okay, what is the resource? Okay, it's a sensor that's collecting the data. So the resource, it will be the server. It will be running COPE server. Okay, the entity getting the information will be the client. Right? Usually in normal configuration, the server is the entity collecting the data, right? It's the other way, right? So simple subscription for a resource and resulting push notifications, and simple caching based on mass age. So we're gonna have a caching also. Okay, like HTTP have caching also, right? So we'll have caching in here, no less. From the architectural point of view, the COPE server will be installed on the end node. Okay, will be installed. The server will be installed at the end node. Remember that very well. Okay, which could be a sensor. On the other hand, the COPE client should be installed on the controller, which manages several end nodes. All right. So usually you have one server and many clients, right? In here, what we have many servers and could be one client. It's kind of different way. All right. So when you look at the protocols in different layers, so for example, in the application layer, you have HTTP, COPE, EB, HTTP, LTP, Simple Network Management Protocol, IPFix, DNS, NTP, Network Transfer Protocol, SSH, and so on. So all of these are application layers. One of them is COPE. However, COPE for restricted devices, for the smart devices. Again, in the network communication layer, IP6, IP4, Rebel, which is used for smart devices, TCP, UDP, UIP, SLIP, okay, 6LoWPAN, all right? These all in the network communication layer. All right, in the physical layer, again, so for example, IEEE 802.11, this is Wi-Fi. Okay, and there's a bunch of them, A, B, G, E, whatever. The 15 series, which is the low devices, the 16 series, wireless HART, Z-Wave, ultra wideband, infrared, PLC, and others, right? So we are using IoT, so we're gonna use, so IP6, 6LoWPAN, UDP is using IoT, Simple Network, the COPE is using IoT, and so on and so forth, right? So COPE features, again, let's take a look at the features. Okay, constrained web protocol, it's constrained web protocol. It's like HTTP. HTTP is a web protocol. It's again a web protocol. Okay, fulfilling M2M requirements. You know what's M2M, machine to machine. IoT, so we don't know the egg is from the chicken or the chick from the egg. So IoT is from M2M or M2M from IoT. Who cares? Okay, security binding to datagram transport layer, security DTLS. We're going to talk about DTLS for security, which is an application level. Then it's asynchronous message exchange. It's not synchronous. HTTP is synchronous. So you have to have connection, establish a connection, then communicate. This asynchronous. So it's kind like every message has a different connection, asynchronous, right? And this fits the nature of IoT, right? And sensors and all of that. Low header overhead, so the header is smaller, and parsing complexity. Okay, what's parsing? When you transfer the data, then you have to read the header, right? From the header, you have get information, so you have to parse through it. This could be a complex process. And if the sensors have to do a complex process, that means more processing. More processing, that means more power. More power means shorter life because it consumes more power, right? Right? So it's less complex, the parsing, right? URI, which is COPE, column forward slash, and content type support. Simple proxy and caching capabilities, so you could use caching. And you know how caching could speed process the browsing, like HTTP, right? UDP binding with optional reliability supporting unicast and multicast requests. So you could have unicast and multicast requests. HTTP usually a unicast, right? It's a stateless HTTP mapping, so you could map it to HTTP. Stateful or stateless is related to the memory. Does it hold the memory or does not hold the memory, right? Allowing proxies to be built, providing access to COPE resources via HTTP in a uniform way, or for HTTP simple interfaces to be realized alternatively over COPE. So you could hook up devices with HTTP devices with COPE through proxies, as you will see. All right, so what we have learned so far, okay? We learned that the application level protocols are very big headers. Like HTTP, the most common one used in the application, might not be suitable for smaller device or smart device of IoT or machine to machine. So we come up with a COPE protocol. It will work like HTTP somehow. It has a smaller header. It's installed in the sensors, and at the sensor it will be a server, COPE server. At the client, it will be at the collecting data client will be as a client, all right? And you always could collect HTTP to COPE through proxies. That's what we have learned so far. So far, we did not look at the header of COPE. Did not look what are the meanings of how it will do the queries. You know what you do with HTTP, how you get the information. Like you have the post, you have the get, right? Post, get, delete, all of these, right? Commands. Okay, we have them here also. We have them, right? Okay. Everybody knows HTML, right? HTML. Okay. All you computer science. Okay. Anyways. So HTTP and COPE protocol stack. So HTTP, any machine, if you have this web server, you have IP in top of IP, TCP in top of the TCPs. HTTP, you could have UDP. However, in the smart devices, in IoT, we have 6LoWPAN. We explained what 6LoWPAN is, replacement for IP6, right? On top of that, UDP, we don't use TCP, okay? And messages and the request for response. The request response and messages. That's the COPE, request and response. All right. So as you see in here, it's replacing things, replacing layers with different layers. So if you compare them, okay. So COPE is network-oriented protocol, using similar features to HTTP, but also allows for low overhead, because the header is smaller, and multicast. HTTP does not have multicast, right? You agree, it's unicast, right? You have to establish the connection, then you could communicate, right? As a unicast. HTTP is based on TCP protocol using point-to-point communication model that not suitable for notification push services. You push the data, push and push. So the sensor will have the data, will push it to where? To the client. Will push it to the client. All right. COPE operates over UDP. Okay. HTTP operates over TCP, right? Usually, COPE is based on REST architecture, and everybody knows what REST architecture. Any programmer, any web developer knows what REST architecture, right? There is REST and there is SOAP. You know, REST architecture, which is a general design for accessing internet resources. COAP provides URI, which is COAP, colon, forward slash, right? Like HTTP column, okay? It provides the REST methods such as GET, right? That's what we do in HTTP. There is GET, POST, okay, get a resource data, post a data, put a new data, and delete. The 4 primitives, right? Any HTTP person knows, you would know it. COAP allows IP multicast, which HTTP does not, all right? Which satisfies a group communication for IoT. What's a group communication? One to many, right? The group communication, all right? COAP defines a retransmission mechanism and provides resource discovery. Resource discovery is not available in HTTP. It's available here, okay? And resource discovery mechanism with resource description. So this is a little comparison with HTTP. So there's extra features with HTTP, and there is extra features with COAP. All right? All right. So COAP structure model. As we said, we have UDP. On top of it, you have the messages, request-response messages, and then the application. COAP interactive model is similar to HTTP's client-server model. So it's a client-server model. However, which one have the server? Sensors. Sensors are the COAP servers. All right? And to use the push model. So the sensors push the data to the client. What is the client? Is the aggregator. Okay? So COAP employs a two-layer structure. The bottom layer is message. Okay? So these are part of the COAP. Message layer. Okay? That has been designed to deal with UDP and asynchronous switching. Asynchronous switching and UDP, right? On top of the UDP. The response request or request response layer concerns communication method and deal with request response messages. Request at temperature, respond with the temperature. Respond to the data and with the data. Okay? So it's a two-layer. So the message layer model. Okay. Message layer supports 4 types of messages. 4 types of messages. The first one is confirmable. So when a message is sent, it needs to be confirmed. It needs to be acknowledged. Okay, confirmable. Okay, then a non-confirmable, which is none. Then acknowledgement, and then reset. When there's a failure, you have to reset. So there's 4 types of messages used. Confirmable, not confirmable, acknowledgement, and reset. Reset the whole communication. 4 types of we'll see examples. Reliable message transport and unreliable. So you could have reliable message transport and reliable message transport. All right? So a person who knows HTTP, and I'm sure all of you know HTTP very well, supposedly, okay? I mean, relate things. Can relate things, how this works and how that, do things, okay? All right. I mean, it would be much more useful, like what we did before speaking about 6LoWPAN to explain IP6. But it took us like 2 lectures to explain IP6. I cannot go on here and explain HTTP. So if you need to refresh your memory, all you have to go to the web and just take one of the pages, talk about HTTP, how it works, what is the features of HTTP, and then try to compare it to COAP. Okay, bottom line, COAP is similar to HTTP, except it's faster, it's a little bit compressed, it's much more suitable for smart devices. Okay, the sensors and IoT devices. So keep retransmission until reliable. Okay, we said we have reliable message transport and we have unreliable. So let's talk a lot about the reliable message transport. The reliable message transport. Reliable means what?
Trusted.
That means guarantee for data delivery, kind of, right? Yeah, reliable. So keep retransmission until remember that we have sensors connected with the client, and sometimes there is disconnection, sometimes there's a problems and all of that. So you could just send it and you don't worry about it. That's what is UDP. UDP does not have guarantee for delivery, right? It's not reliable. Okay. So to have it reliable, what you have to do, keep a transmission until you get the ACK with the same message ID. So for example, it's a confirmable message. This is a message ID 8C56. Wait, keep the message until you get the acknowledgement. So the acknowledgement will have the message ID. So this is a confirmable what? Message. The message is confirmed. Is confirmed. Okay? Using default time out and decreasing counting time exponentially when the transmission the confirmable messages. Okay, if recipient failed to process message, it responds by replacing acknowledgement with rest. So you're gonna send it. Okay, you set up the timer until hopefully within the timing period you're gonna receive the ACK. Okay, if it does not, okay, it will send the reset the whole transmission. Okay, but you have to get confirmation. Okay, for the transmission. Unreliable message transporting with non-conformable time message. It doesn't need to be acknowledged. So you send the client to the server, okay, and you don't need to confirm it. Okay, there you don't wait for the acknowledgement. But has to contain message ID for supervising in case of retransmission. In case you did retransmission, you receive a duplicate package, you need to know where is the duplicate package. So always you have to include the message ID. If recipient failed to process message, server replies, okay, with reset the transmission. So we spoke now about, remember, let me go back. So we spoke about messages. There's two kinds of messages, reliable and not reliable. Okay, conformable, not conformable. And then now go to respond and request messages. Okay, so it has a piggybacked. What's piggybacked? Acknowledgement message also has information from the previous communication. So it's like piggyback, you have a value, okay. And separate response and non-conformable request and response. So there's three types. So the piggyback in here, client sends request, use a conformable type or non-conformable type, doesn't matter. The client sends conformable, not conformable, right? Okay. And receives response acknowledge with conformable message immediately. So you send, this is conformable message, get temperature, and there's a token. You get a response, the acknowledgement, which includes the same message ID, okay, 2.5 content, token, okay, which is 20.1 centigrades, for example. Okay, so that's the token number, okay, the token number and all of that. Okay, for a successful response, ACK contains response message, okay, identify by using token, For failure response, ACK contains failure response code. So in here, it sends, okay, the data is same thing, but in the failure, did not get the response. So after a while, we'll send acknowledgement with not found token and and until the message not found. All right. So in here it sends, okay, and here, this if you did not get it within a time, it will send the message with information that it was not found. All right. Every message has to have the message ID. Every transportation with the ACK and with the message, it has to have the message ID. It helps in sorting. If they arrive out of sort, it will help in different issues. Okay, so the second technique is separate response, right? So we piggyback it, backed and separate response. So in this, if receiver receive a confirmable type message but not able to respond, this request immediately, it will send an empty acknowledgement. So it will send a confirmable message, requesting for something, but it cannot respond right away. So what does it do? It will send an empty acknowledgement. It will here. It will send an empty acknowledgement. Only contains the message ID without information, without the token. Without the token. Kind of telling, okay, I received your message, okay, but I cannot send it right now. All right. Then after a while, when it's ready, it will send back the message with the token. Okay? Again, send the message, send the request, the message ID with the token requested, but it could not send it on time. So just send an empty acknowledgement. I received it. It happens to all of us, right? Somebody send you an email. Myself, I do it a lot. Somebody send me an email needing something. Then what I do? Reply, I don't say anything in the message. What does it say? This is my message. I received your message. I received your email. That's it. So he will understand that, I received it. So when I'm ready, I respond. Right? Same idea here. Okay? So when server ready to respond, this request, it will send a new confirmable to the client, and the client reply a confirmable message with no acknowledgement. ACK is just to confirm confirmable message, no matter confirmable message carry request or response as you see it in the figure. Does not make a difference what you carry, response or request. So this is separate response. You can have a sample. There is non-confirmable request and response. So it's not confirmable request. So I see unlike piggyback response carry confirmable message. In non-confirmable request, the client send non-type message indicating that the server don't need to confirm. So since here it says non-confirmable, the message type within the token, but it's none. That means you don't have to confirm. Okay, you don't have to confirm so the server, when he responds back, it will send with non-confirmable type message, as you see it in the figure. Alright. So now we learned about the two layers. There's messages and there's response and requested response, right? So the message could be reliable and unreliable. We saw that, and for requested response, there is different. There is piggyback, no response, and with response, right? So different modes of operation. All right. It's suitable for IoT because the devices will be in different situations. All right. In different networks. Some networks are reliable, some of them are not reliable, some of them you need to confirmable message, some not, not confirmable message. If you really don't need to have the message confirmed, that's good. You reduce the amount of the acknowledgement transmitted. That will reduce the. Remember, your goal always to reduce the amount of the transmission, because for every extra bit you send, you're consuming more power, right? So that's what it is. So far is just by having different, we try to manage the transmission as needed, right? The whole trick is in reducing the headers, the information, right? And the size of the headers and processing time. The processing for the headers, right? Parsing, right? We reduce the parsing complexity. Okay, because any packet will be received, it needs to be read and needs to be processed. Okay, so that's a. So let's take a look at the message format. Okay, so COP is based on the exchange of compact messages. Compact messages, by default, are transmitted over UDP. So we always use UDP. TCP is a big problem, right? In the previous class, I explained that how the message goes from the application layer will be encapsulated in transport layer, and so it becomes bigger, fatter, right? Right? So we start with the HTTP. We need to compact it, and we need to send it over UDP, which is a shorter header. Okay, shorter header, and it's not reliable, right? Shorter header, not reliable. So where we get the reliability from? Not through the transport layer, not through the UDP. We give it from where? From COP, right? If we need it to be reliable, we send reliable COP message. Okay, COPE reliable message, right? Got it? So, i.e. each COPE message occupies the data section of one UDP data program. We already explained this morning, encapsulated, all right? Message of COPE uses simple binary format. Simple binary format, that means less complex, it's just a binary. You're processing a binary data. Right? You don't have to do XOR and adding and all of that to understand what's the meaning of the header. Simple binary format. You got it? So that will reduce the complexity of the operation, right? So message, fixed size, the message, okay, fixed size 4 byte header. So fixed size 4 byte, no matter what. The size of the COPE header is 4 byte plus variable length token. You know the token? You know what I'm talking about? The token? Token. Variable length token. The data. Okay, temperature, whatever. And the sequence of the COPE option. Why you need the sequence? If it comes out of sequence, you could order it at the destination. If there's a duplicate message, you know there's a duplicate. So if you send 2 messages with the half sequence number, then these are duplicates. These are duplicates, right? All right? And then we have the payload. What's the payload? The data. Okay, the data payload, okay? So when you look at it, like you have the version, we'll take a look at TOC code, message ID, okay, message ID, all right, message ID, message ID, message ID, right? Okay, and then we have the token, if any, token, okay, and then the options, if any, and the payload, if any. Option, 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 option. So these are the basic things. So COPE option format, COPE option format, option number, option delta plus EX, X option number. So option delta X option number, okay, in here, for example, option delta X option number, it will pass in here delta option and delta options X option. So when you have the options will be included, in the message. Security protocol and applications for COPE security. Okay, there are 3 main elements when considering security. Anybody taking network security with me this semester? Yeah. Anybody took it before? One. Anybody know anything about security? Okay. So security is, there is integrity, there is authentication and confidentiality. You take in the class, explain it. So, integrity?
Integrity means that the information should not be changed by an unauthorized party.
Exactly. So the message is integral. Nobody has changed it or altered it. Okay? Authentication?
That means that the person that sent the message should be, how do I put it? For example, if I send a mail to you, you should know that I'm the one that sent it to you.
Okay. So the message is authentic. If I send you a message telling you there is no class next week, so the message should not be secret. But did I send it or your colleague is trying to screw you up? Okay? So it has to be authentic in the message, right? Then?
There's a mistake.
Confidentiality.
Confidentiality. Is integrity, availability, and confidentiality that we did, not authentication. Authentication is somewhat part of confidentiality.
No, confidentiality to be the message secret. Nobody can read it except the person who receives it. So if I'm sending you a message to you,
only I should be able to.
You should be able to read it. That's confidential.
The amount of availability, that is, the message should be available when you need it.
When you need it, yes. When you need it, that nobody can, like for example, people could run deny or something, remove the availability. Okay? Thank you so much. You see, a product of my class in network security is knowledgeable, right? So we use DTLS can achieve all of the 3. Integrity, authentication, confidentiality. You know who is the most benefiting from these classes? I'm the camera person. He's taking classes for free. So
Getting paid.
So actually, my student, the person was recording my classes from business last year. For the past 2 years, he just graduated, was replaced by him, and he's applying for a PhD program in business field. And he wrote, the background they have in Python and network security and all of that, because he's been recording this for many times that he is very knowledgeable about these fields anymore, which is kind of nice. Some people, they don't want to learn, just and he's from business background, so it was so DTLS employs TCP, which is too complex, DTLS. So DTLS solves two problems: reordering and packet loss. So there's a lot of problems when you do transmission. What if you receive them up? So usually when you transmit, okay. For example, if we need to go to New York, so all of us leave at the same time, okay. But some of you will arrive before the others, right? So we need to reorder. That's why we have the sequence numbers, right? And also, what we have packet loss. What will happen if the packet lost? Who's gonna report it? Which packet is lost, and all of that. So DTLS take care of this problem. It adds a 3 implements: packet retransmission. So the packet lost, you gotta do retransmission. Assigning sequence number within the handshake, okay, sequence, and the replay detection. What's replay detection? Replay, if I'm sending a message to a person, to Sarah, let's call her Sarah, okay, all right. So and he gets the message. Let's call him George. George get my message and he take it and replay it in the wrong time. Okay, so I send her a message. I'll tell her, let's meet in my office today. So he takes it and he sends it to her on Sunday. Looks from me. She will think it's authentic. She comes on Sunday to my office, and I'm not here. And who is the problem? He did George. He did replay for my message and it prospered to the cloud. So replay. That's replay. One of the problems we have in security. Replay. Somebody replay the message. All right. So DTLS will add these elements. So security protocol and application for quote. Unlike network layer security protocol, DTLS in application layer protect end-to-end communication. So implement DTLS. First of all, COAP runs in the application layer. DTLS also runs in the application layer, which provide end-to-end communication. And so this node, right? Like let's say that you have communication between this computer and your mom in China. So computer to computer, end to end. But it's gonna go through many switches, through many routers, until it gets to all the destination in India, for example, right? Okay, so we are here, we guaranteeing the end-to-end security as if there is nothing in between. As if they are directly connected with a wire. So end-to-end. Okay? Guys, that's what is end-to-end communication, security, right? As if there is nothing in between, as if they are connected directly. Okay, end-to-end. Okay? And this at the application level. Okay? So no end-to-end communication protection will make it easy for attacker to access to all text data that passes through a compromised node, right? Because not only the ends could be compromised, the routers could be compromised, all the switches in between could be compromised, okay, all the subnodes would be compromised, right? So when I have end-to-end security, that means no matter how many are compromised in the middle, they cannot get to the message. So providing end-to-end security is very important, okay? Because it will be encrypted at this end, it will be decrypted at where? At the last end. It's different than it's encrypted, decrypted, and encrypted again, decrypted, encrypted again, decrypted, right? We're talking about end-to-end security. Okay, end-to-end security. Okay, DTL also avoids cryptographic overhead. Cryptography is a processor, consumer, memory consumer. Okay, and that's why we studied like in the cryptography. There's multiple, multiple algorithms. Nowadays, trying to move from software-derived algorithms to hardware implemented because. Even now with the hardware, I mean, in new motherboards, you could enable the BitLocker, right? You call it BitLocker, which is encrypting everything in the hard disk. So you could enable it, you could disable it. When you enable it, what do you notice? The computer becomes slower. Why? Because whenever you need to read the packet stored in your hard disk drive, what do you have to do first? You have to unlock it. Whenever you need to write, you have to encrypt it first. Encrypt, decrypt. So it's a process, right? So DTLS also avoids cryptographic overhead problems that occur in the lower layer security protocols. Anyways, so DTLS in the protocol stack, how it works. So we have the physical layer, so for example here, the ZigBee, whatever it is. Then we have the IP6 network, then security. DTLS is between where? Between the application and the transport to provide end-to-end security. All right? Remember, in my opinion, nowadays, having IoT devices secure in communication is much more important than even your PC. These devices will be controlling your garage door, your house door, your sugar level diabetes machine. You'll be monitoring your life, right? Okay? So everything. So can you imagine somebody hack? So people now, for example, if they have a problem, device, the doctor could log in, could inject you with some medicine. Can you imagine somebody hack into this IoT device and inject you once for good? Okay, all right, it's a problem, right? Okay, or somebody hacked your camera at your house,
And it's watching it.
watch you doing whatever you are doing, or open the garage door for security is the issue. There is no IoT without security, all right? Without security, would you accept to have any of these devices in your life without making sure it's like end-to-end 100% security, right? So it's an issue, right? So security is in here. Somebody comes to us, why you have to, just the sensors. Why you have to worry about? Some applications, if you're reading the temperature on the Mars, why it have to be secure? Yeah, okay, that's fine. This is, that's for analysis. Remember what we said, IoT is all about? Data. And the data we use it for analysis and we use it for real life applications. So it's a very important issue, and that's why I chose, by the way, for your projects to work in security. I wanted you to hit two stones, two birds with one stone. So security and IoT. Okay. So, anyways, so structure of DTLS, which is a layer between the application and the transport. There are two layers of DTLS. The bottom one contains record protocol. The top one includes the three protocols, which are alert, handshake, and application data. 3 levels. Okay. In some condition, change cipher spec protocol may replace one of them. Change cipher spec message is used to notify record protocol to protect subsequent records with sub-negotiation, cyber suit, and keys. Record protocol protects application data by using keys generated during handshake. So we're gonna have a handshake. Why handshake? To exchange keys. So for security, for encryption, okay, you need to have keys, sender and receiver, right? So you have to have a handshake to receive these. Then after that, you have to do the encryption for the application data, and sometimes you need to have alerts if there is, problems and all of that. So structure of DTLs for outgoing message protocol, you divide. Okay, what you do with the message going, you have to divide it to the right size, right? Then you have to compress it, then you have to encrypt it, and then you have to apply message authentication code, MAC. What is a message authentication code? It is like you create a MAC digest from the message with one of the hash functions. So when the receiver receives it, what does it do? Create the MAC again and compare the sent MAC with the calculated MAC. If they are equal, then the message is authentic, is integral. If they are different, then it was altered. So 3 things again: the message authentication code, the encryption, the data will be encrypted and compressed and divided. 4 things. For incoming message protocol, so this is for outgoing. For incoming, what you have to do? Divide, that means the message was divided and sent in multiple pieces, right? So what is the first thing you have to do? You have to build a message. So what you have to do? Reassemble. You divide, you reassemble. Compress, what you have to do? Decompress. Okay, encrypt, you have to decrypt, and you apply the MAC, you have to verify it, is that correct? Right? Again, for the message, you have to do 4 things. For that, when you receive it, you have to do 4 things. Reverse it. Clear? Structure of DTLs again. Record header consists of 2 parts. Content type. Okay, content type decides what is constrained in a fragment field. What is the constraint in the graph field and the fragment field? So, you know, when you have a longer message, what you have to do? Fragment it. Okay, and somewhere when the message is fragmented, you have to tell that where in the header. This message is fragmented. And what is the offset? So let's say if you have a message like 12 bytes. So the first one is 4 bytes, the second one is another 4, the third one 4, or 5 plus 3 or plus, right? You have to know the offset that you could build it again. You could build it again, right? Okay, handshake protocol is rather a complex one which involves in a lot of exchange steps. Process of handshake, okay, compared with DTL's record, handshake protocol is rather a complex one, involves in a lot of exchange steps, and individual messages are grouped into message flocks. So you have from here, client hello, hello verify request comes in here. It's handshake, you know. Then client hello one more time, and then we'll send in here server hello, server key exchange the keys, because you know they have to, everything of that will be encrypted. Then server hello done. Goes back like this, client key exchange, change server spec, and finished. Then change again and then finish. So there's a process of handshake to establish the communication and exchanging the keys. Right? Got the general idea? Okay. So unicast communication model. Okay. So the architecture shown below is for unicast communication. Client interacts with one or more servers. What is servers in here? The nodes. Okay, what the client is, the recipient. So the client also needs to know which certificate, or so what will happen in here. So for example, in here you have, you know, this is a client, okay? It connects to IP based network. Multiple servers could interact with. So server A, it could send the identity, the key, the public key, you know. So sometimes you need to connect to a certificate server to create the keys to exchange between for communication, right? A third party, all right? So this is an example for COAP application for smarter home. For example, in here you have, for example, where is the data collection node, sensor. So this will be connected with COAP to the control server. So this is a server. The node is a server. Server, this is a client, right? Then it could go to the database server, to the web server. Now, the web server here, with the web, so you, from here, you are reading here what you are using, HTTP for example. But when it goes down to here, there is a proxy that could convert the HTTP request to COAP request. Okay, COAP request, all right? In here, in this line, it's like a regular network, so you could use HTTP, HTTPS, there is no problem. But in this network in here, we're gonna use the COAP application. So COAP application for a smart home in system networking data collection nodes consist of one proxy, smart socket, and wireless data collection nodes. Energy information and environment information of requirements is collected by the smart socket there, and will be collected. Anyways, another older technique than COAP is MQTT. Okay, MQTT. Okay, so both are used, but COAP is much recent. So MQ message queue transmission is a publish subscriber message control designed for lightweight end-to-end communication. So it was before COAP even, I think. MQTT has a client-server model where every sensor is a client. In COAP, every sensor is a server. In here, every sensor is a client. A client and connects to a server known as a broker over TCP. So the broker over, so client C, client, so sensor, they are connected to a broker. A cannot communicate with B directly. They have to go through the broker. Okay, a broker. So, MQTT is a message-oriented. Every message is discrete chunk of data, back to the broker. Every message is published to an address known as topic. So you could have multiple topics. So every message will be added to a broker. We call this broker a topic. Okay, we call it a topic. Clients may subscribe to multiple topics. That means that they might subscribe to multiple brokers. Call it topic. That's the term, topic, right? Every client subscribed to a topic receives published to the topic. So if A sends a message to the topic, everybody will receive it. As long as you subscribe to that broker, everybody will receive it. How you know it's for you or not? From the destination address. Okay, so you see there is a weaknesses and there is, broker can receive all of that. All right, so a simple network, a simple network with 3 clients and central broker. All the 3 clients open TCP connection with the broker. TCP connection. Clients B and C subscribe to the topic temperature. So this is subscribe temperature. So to the topic temperature. So at a later time, client A publishes, what is client A here? Publishes a value of 22.5 temperature, for example, for a topic temperature. The broker forwards this message to all subscribed clients. So it publishes to here, but anything published to the broker, it will be published to all the clients. Okay, so you publish to, and will send it to all the clients. The broker receives and sends to all the clients. The broker forwards the message to all the subscribing clients. The publisher subscriber model allows MQTT client to communicate one-to-one, one-to-many, and many-to-many. All right. So the main work that you have to have this broker. Okay, to have this upload. Okay. So there is something called topic matching. Topics are architectural, like filling system. Okay, so you have like kitchen, oven temperature. Okay, wildcards can be used. Okay, for that. It could provide a quality of service. So MQTT supports 3 quality of service levels: fire and forget. Fire means send and forget. You don't have to be to be confirmed. Fire and forget, right? They're also delivered at least once. It has to be delivered at least once, and delivered exactly once. And you know what's the quality of service, right? Quality of service, just what kind of service and the quality. For example, in the regular network, you could configure the switches for a certain quality of service. So, for example, I would like to guarantee a certain bandwidth to this lab. So by configuring the ports in the switches, it will have a certain, minimum bandwidth to this lab, for example. Let's say 100 megabits per second. All right? Quality of service, yes.
What is the difference between delivered at least once and exactly once?
So delivered, it will be once, twice, 3 times, 4 times, and this is only 1 time. Okay? So there is no quality of service, right? Okay, has second level, third level. Okay, so kind of guarantee the last will and testament MQTT clients can register a custom last will and treatment message to be sent by the broker if they disconnect. This material can be used for single, so okay, anyways. Also persistence, okay, security queue broker may require username and password authentication. To ensure privacy, TCP connection may be encrypted. So remember that the communication in the broker in here, I'm sorry, the communication in here is using what? TCP. TCP you could implement SSL and TLS security. You don't have to have a special application for security. It's a lightweight application. It has two drawbacks for very constrained devices. Every MQTT client must support TCP and will typically hold connection open to the broker all the time. So it's synchronous connection. The connection will be open all the time. That means what? Consumption, is that right? Okay, for some environments where packet loss is high or computing resources are scarce, this is problem because you will consume the power more. MQTT topic names are often long strings which make them impractical for the smart devices, low LLMs. Both of these shortcomings are addressed by MQTT TSN protocol, which defines the UDP mapping of MQTT. Anyway, so we have two protocols in the application level, which is MQTT and the COPE. COPE is a much more suitable for IoT devices and could provide more. So this way, I put some references. I just gave you the rough ideas, but we could go over the references. So today we have covered two protocols in the application level, actually three, right? Which is HTTP, not HTTP, COPE, MQTT, and the DTLS, right? The security. All of these work almost in the application layer. The other lectures will cover 6LoW and Ripple. Next time we're gonna go over ZigBee. We're gonna go a little bit in the physical layer, cover some of the technologies, okay, and explain it. Thank you so much.